Okay, so I've had a couple questions about problem 5 in the pre-lab for I think this is lab 9 maybe. And since I'm not going to be around on Monday because I've got to teach at the high school, I've decided to put together a little video explaining how to solve this problem. So what problem 5 asks us to do is it asks us to determine the Thevenin equivalent voltage and resistance in terms of a measured voltage and current, taking into consideration the internal resistance of the voltmeter and ammeter. So to see how we would do that, let me first draw a circuit diagram for the measurement of the voltage. So what we have is we have our Thevenin equivalent voltage that is in series with a Thevenin equivalent resistance. And we measure the voltage between points A and B with the voltmeter, which has itself some internal resistance, which I'll call capital R with the subscript int for internal. Now, to solve this, the first thing we need to realize is that the voltmeter is going to measure the voltage between points A and B, and that is going to be equal to the current that flows through this circuit times the internal resistance of the voltmeter. Okay, that's the voltage drop between points A and B. Now, we need to come up with some kind of way to find the current then. And the way we do that is we use the loop rule. So the idea is if I start here in the circuit and I go around in a loop like so, the total voltage drop should equal 0. So delta V is equal to, well, I gain a Thevenin voltage when I go over the EMF source there. I lose voltage I times Thevenin resistance when I pass over the Thevenin resistor, and I lose I times R internal when current flows through the voltmeter. So now if I simply solve for, and that has to equal 0 volts. That's the loop rule. So now if I solve for the current, I find that the current is equal to the Thevenin voltage divided by the Thevenin resistance plus the internal resistance of my voltmeter. Now taking that number, or that expression, and plugging it into this equation over here on the left, we see that the voltage between points A and B is equal to the Thevenin voltage times the internal resistance of the ammeter divided by the internal resistance of the voltmeter, plus the Thevenin resistance. So we get this expression right here. Now, the thing I want to point out about this expression, a couple things I want to point out about this expression. The first thing is that there are only two unknowns. We don't know the Thevenin voltage and we don't know the Thevenin resistance, but we do know my voltage that I measure between points A and B and the internal resistance between inside the voltmeter. The other thing I want to point out is that in the lab we consider the internal resistance of the ammeter to be infinitely large, and I want to show you that when we take that limit, that we do see that the voltage between points A and B is just equal to the Thevenin voltage. So to see that, if we look at the denominator down here in this fraction, when the internal resistance becomes very large, the Thevenin resistance is comparably much smaller. So the Thevenin resistance in this limit goes to 0. We now have Thevenin internal resistance divided by Thevenin internal resistance. So this whole thing in the parentheses here, this goes to 1. And so we just have that the voltage between points A and B is just equal to my Thevenin voltage in this limit. Okay. So that's the first equation that we get. The next equation we get from considering what happens when I measure the current between points A and B with the ammeter. So let's go ahead and draw another circuit diagram for this one. So we have our Thevenin equivalent EMF source, and we have our Thevenin resistance. And then we connect our ammeter between these points, A and B. And it has a resistance I'm going to call lowercase with a subscript int. And the idea here is that the internal resistance of the voltmeter is much larger than the internal resistance of the ammeter, hence the notation of using a large R for the internal resistance of a voltmeter and a lowercase r for the internal resistance of the ammeter. So once again, we're going to use the same kind of trick. There's a current that flows around to this circuit, and around one full loop there is no voltage change. So we have that my Thevenin voltage minus the voltage over the Thevenin resistor minus the voltage drop over my internal resistance of my ammeter has to equal 0 volts. In other words, my Thevenin voltage is equal to the current that I measure times the Thevenin resistor, forgot to put the T there, plus the internal resistance of the ammeter. Okay? So these are our two equations that we have. We have this equation up here. Let me put that in a box. And we have this equation that I just found down here. Notice that in both of these equations there are only two unknowns. We don't know the Thevenin voltage and we don't know the Thevenin resistance. I know the current down here because that's the current that I measured with my ammeter. Okay? I also I know my internal resistance of my ammeter, and I know the internal resistance of my voltmeter. Okay, I'm not asked to find either of those. So we're in a situation now where we have two equations and we have two unknowns. So it's just a matter of solving a system of equations to find what the Thevenin voltage is and the Thevenin resistance is. Hopefully from this point you'll be able to finish solving the problem. I don't want to go through and completely solve it, but I think this will explain it, or hopefully answer any questions that you have. So if you still have any more questions about any of the problems in the pre-lab, or you don't understand any of this, please send me an email, let me know. Also, if you could please let me know how useful you found this video. I'm thinking about doing something like this for the high school class that I teach. Probably not this year, but maybe next year. So if you find this useful, please let me know. Okay, and have a nice break. Bye.